All right. So, yeah, first I would like to thank the organizers. This is really nice. Wonderful workshop. Sorry. And so what I would like to talk about is how to learn a basis from certain types of measurements, and I'll explain what it means to learn a basis. And I'll sort of try to explain why you may want to consider such a problem and how to do it efficiently. And this is joint work with my colleague Louis Rademak and our student James Woz, who really did a fantastic job on this. Okay, so well, let me first sort of briefly summarize. So first I will propose an algorithmic primitive for hidden basis recovery. I'll give some examples of where it can be used in some applications, and one of them is new, but I won't have time to really describe it, the application to spectral clustering. Then I'll say a few words how to do it. And then I'll talk about analysis, and in particular the perturbation analysis, what may be considered some sort of nonlinear generalization of the Davis-Cahan theorem for matrices, for matrix perturbations. Okay, so first let me start by telling you what does it mean to recover a hidden basis. So suppose you have an orthonormal basis E1 EM, and it's okay to have a partial. So when I say a basis, I'm fine with a partial basis. For example, even one element for me is a basis. You can define, we define the basis encoding function f of u to be the following. So you take in the product of your input vector with each of these basis elements, and you apply some nonlinearity to that, this g. And then you just sum this up. So this is the basis encoding function. And the sort of the primitive would be given evaluation access to f and the gradient of f to recover the actual basis. Okay, so that's the setting of the problem. That's what's interesting to me.
Can you choose the use, or can you decide which u, or do you also do this?
So typically you assume that EI are unknown, so the problem is to recover EI, and U is just an arbitrary vector. So yeah, you can choose it in principle. You mean something like active learning? Yeah, why not? You can do that. I guess it depends on your setting. So okay, so that's, and G, we may or may not know what G's are.
You know or unknown?
So you are given access to this function, so we can assume that given a u, you can compute this function. And typically I'm interested to for values of this function on the sphere. Okay, so we're giving this. The question is how to recover EIs. So why is this an interesting problem? Well, let me point something out. Very, very basic. So just think about standard spectral analysis of a matrix, right? So if you have a matrix, you can write a quadratic, so let's assume a symmetric matrix. You write a quadratic form, UAU, and you write it in terms of its eigendecomposition. So if you write it in this form, then f of u, this quadratic form, is just equal to sum lambda I, u in the product ai squared, right? That's the spectral theorem. And if you sort of think about going back to the previous slide, this is a basis encoding function with gi just being lambda I t squared, when the lambda I is a corresponding eigenvalue for vector ei. So you can view the spectral theorem as a special case of this basis encoding. And if you have this kind of function, right, what would be the question of recovering the basis? This is just recovering eigenvectors and eigenfunctions. So that's obviously a very important algorithmic primitive, computing eigendecompositions. Now, a more general case, or which recently people have been quite interested in terms of specifically applying it to analyzing recovering parameters of models and machine learning, is tensor decomposition. And basically what you have, if you have a certain kind of tensor, this rather special tensor, you can actually also write it in terms of a basis encoding function, and what you get, you have f of u is equal to sum gi u in the product ai, with the gi's being wit to the 4. So the basis decomposition, diagonal tensor basis decomposition is a special case of this BEF. A more interesting example, which is also well known, is independent. Well, I don't know, more interesting. It's equally interesting. In fact, this is a special case of the previous one in a certain sense. Is independent component analysis. I am not going to describe what independent component analysis is. Basically, if you have some sort of mixture with independent coordinate, the question is how do you recover it, giving some linear transformation of that distribution. And it turns out that you can recover it by setting a basis recording function, and if you play with it, you will see that the basis recording function has a form, if you are using the fourth cumulant, it's something like the fourth cumulant of a directions times t to the 4. This would take a little bit longer to describe, but that's one way to rewrite it. And there are some interesting, there is a work by Su and Kakadi when they provided an algorithm for estimating parameters of a spherical Gaussian mixture model. And it turns out that that can also be written as a basis encoding function, sort of equivalent rewriting. And finally, I'll skip this, but this is, you can also show that multi-way spectral clustering is also an example. You can kind of reformulate it in this form. And in fact, you can apply it to practical data. We've tried that. OK, so that's kind of the justification that, well, perhaps it's an interesting primitive, right? Because you have a bunch of interesting things people have done, or some new things, which can be rewritten in that form. Now, how do you recover it? OK, so this is great. This is, perhaps I have convinced you that this is an interesting problem. Now, what do you actually do with this? Well, so here is the algorithm, and this is a slightly simplified algorithm. You have to do a little bit more to prove theoretical convergence, but if you just want to use it in practice, this is actually fine. And what we call gradient iteration. So what you do, you do the following. You take a point on a sphere, u. So we are primarily interested in the values of the function on a sphere. So you take a point on a sphere, u, and you apply the gradient to it, right? The gradient of this function is a vector. So you can, if you scale it, you can think of this vector being another point on a sphere. So what you do, you replace u by gradient of u. That's basically all there is to it. And it kind of may look a little bit strange. And then you repeat this, of course, until you get some sort of convergence or until some sort of criterion is satisfied. And you may think this is a little bit strange, but actually, if you think about just ordinary matrix power iteration, and if you go back to this example when f of u is just equal to u in the product au, this becomes au divided by norm au. And that's the standard matrix power iteration. So this is a generalization of the power of the classical matrix power iteration. And in fact, you can show that this is also a generalization for a tensor iteration which have been used recently. So that's a kind of algorithm. OK, now, what do you want from this, right? So you want this iteration to basically converge to something which is, has good properties, and you want to somehow bound the number of iterations. So, okay, well, obviously, to say something reasonable about this, if you go back and look at the basis encoding functions, you need some sort of conditions on GIs, right? Because you have, if you recall, let me just write it down so you can compare f of u with sum over I equals 1 to m, gi u e I in the product, okay? So in general, if you don't have any conditions on G, it's very hard to say anything specific about this because, well, it's not quite an arbitrary function, but it is certainly a rather large class of functions. So what we need basically the following. We need that gi of square root of x is strictly convex on 0 and 1. And it's kind of a strange condition, you may think. I'll explain a little bit where the square root of x is coming from. And then we need this as a technical condition. It's not strictly speaking. This is not so important. This is the kind of crucial one. And you can see that all previous examples satisfies both of this. Okay, well, so suppose I have this. Then I can prove the following theorem. So under these assumptions, on the constant functions gi, the set of ei plus or minus, so there is some sort of indeterminacy up to sign. Yeah?
In your example where you had the u inner product with au, these gi's were simply quadratic, right? So gi of square root x is not strictly convex.
That's a very good point. So actually the classical spectral theory is a limit case of our framework. It doesn't, strictly speaking, satisfy. So I should, it's not completely correct, right? So it's a limit case. And I actually point out the difference. It makes a difference. Because you don't get quite the same thing. In fact, well, I'll get to it in a second, what the difference is. So the set of ei, the hidden basis vectors, are the only local extrema, or maxima or minima of f on the sphere. And each one of them, each one of them is a local extremum, and there are no other local extrema. And that is kind of interesting because this is it's a slightly unusual situation, right? You have, what you have a non-convex function, but yet you have a very sort of satisfactory enumeration of its maxima, right? Usually for a non-convex function, that's kind of, well, anything goes. But this is, there is some special structure to this. Okay, so that's, what happens when this is not strictly convex, actually? That's, to address the question. Well, if you have that this is convex but not strictly convex, then if you think about what happens for AXX, there is only one local maximum, right? The rest of eigendirections are not actually local maxima. They're only local maxima in the correct plane. So that's what the strict convexity is important. So it's kind of, you can kind of think that it degenerates, and at this point you only have only one local maxima. Here you actually have m local maxima, the same as the number of your directions. Okay, so now let me explain a little bit, because this is kind of a strange thing, right? You have this description. And I would like to point out that there are lots of other critical points, exponential number, actually. So here is what we call hidden convexity. And the idea is the following. Well, it's kind of a simple idea. So suppose you just have a point on a sphere, right? Then if you take a square root of each coordinate on a sphere, you get a point whose coordinate sum to 1. Right? Because on the sphere you have the sum squares of coordinate sums to 1. If you take square roots, you get the sum as 1. So if you write a vector as u equals xi ei, if you write it in this hidden basis, and you apply this transformation to that vector, then what you have a map from the sphere to the simplex, if you take the square root of each of the coordinates. Now, if you think about what happens here, you can consider the following function. So suppose I take g of u to be sum gi, square root of uei. So I'm taking square roots of this. Okay, let's not worry whether it's positive or negative. This function is actually very similar to the original function. And you can see that the maxima of the original function correspond to maxima of this function. But now this function is actually convex on a simplex, because each of g of square root of x is convex. So now I have this function which is convex on a simplex. And And the maxima of this function corresponds to the maxima of the original function on the sphere. So this requires a little bit more work. I'm oversimplifying slightly, but that's basically the idea. Now, what about local maxima of convex functions, right? It's kind of a strange thing. The local usually people in convex optimization, typically what you do, you take local minima of convex function, right? Here I'm saying something about local maxima, but of course local maxima of convex function on a convex domain are not too bad. They take the maximum value on the extreme points of the domain. If it's a simplex, the extreme points would be just the ends, well, whatever you call it, vertices of the simplex. And in this case, there's 2 points. So what you can show is that after this transformation, the maxima of the function, of this transformed function, will be at this point. And therefore, the maximum of the original function will also have to be at this point. Now, of course, you don't actually know. You cannot write your function like this because this is unknown. But what you can look now, you have a correspondence between the maxima. So that's basically the idea for this result. So that's the point that there's a maximum. Typically what you do is minima on the convex domain. That's why you have actually not a unique minimum, of course, but you have m maxima in this case, because there are exactly m vertices. Okay. So that is kind of, that gives some intuition for this result. Why are the only local extrema of f at this point? Now, what do you actually do? Well, you don't just want to say, so once you know this, you already can do something. For example, you can run gradient descent, but, or ascent. We would like to show something about this gradient iteration. And it turns out that what you can show about the gradient iteration algorithm is the following. So the set of stable fixed points of gradient iteration is exactly EI. So that's the kind of first result. Second, a gradient iteration. And here you have to, I am sort of cheating a little bit because you have to do some sort of intelligent restart. You can recover all hidden bases efficiently, and I'll talk a little bit more about what this means in a second. And finally, what you get that if gi of square root of r square root of t are convex, so this is a stronger condition when r is bigger than 2, then convergence of gradient iteration is of order r minus 1. So for example, if you have cube root, so if gi is equal to gi of t is equal to t cubed, then the tth root, which is the third root, will be convex. Well, then you get convergence, quadratic convergence. So that's much faster than the typical convergence for matrices. Yeah?
So if, looking at theorem 3, if I just run this with full vectors and orthonormalize it every iteration, will I get all of the vectors simultaneously?
Orthonormalize what after iteration?
The set of vectors, right? I could run this with u1, u2 through um simultaneously and just repeatedly orthonormalize, right? That's how we usually do power iteration.
I think you can do something like that. I need to think a little bit, but I think it's quite possible that you would get the full one. But it's a little bit tricky because you have to do these restarts. Yeah, so that's the interesting thing, and that was observed before about tensor actually, in the tensor case, that you get superlinear convergence for tensors. Okay, so now let me briefly describe the perturbation analysis. So first, what is the model? Well, the model here is very simple. You just add some noise to your function. And you have to control, so instead of measuring the basis encoding function, you're measuring basis encoding function plus some e, where e is basically your noise. And you have to control the derivative to be able to say anything about the algorithm. And in fact, if you want to analyze it, you have to control the Hessian. So that's a kind of condition. It may look pretty restrictive. It's actually not so restrictive. In all those like ICA, you can control this. In fact, we have a result for ICA, for example, on perturbation stability. And one more thing here too, if we want to have some analysis of the perturbation, we have to quantify convexity of gi of square root of x. So it's not enough to say that this is convex or strictly convex. We basically have to say, well, how strictly convex? And there are a couple of ways to do it, but one way is to say that gi of square root of x prime prime, right? Oops. If, you know, for convexity, it's enough that it is greater than 0. But if you want to have some sort of quantification of it, you have, well, to say more specifically, say it's between these two monomials. And here we have to be, it's a little bit tricky because this power can actually, so delta, for example, is bigger than 0. So this could be something like x to the minus 1. So to sort of make it simple, let's just say that gi of x, just a little bit of x squared would satisfy this. You need a little bit more than x squared. Okay, well, so here is the kind of result we get. So we show that gradient iteration recovers the vectors e1 to m up to error basically, which is, you know, in the simplest case, you can imagine that, well, this depends on m, and it depends on this delta. But say if my gi is x cubed, it's just going to be m to the 1/2 times epsilon. So that's the kind of bound that you get. So that basically becomes this for the x cubed. Well, what do we need? Well, we need the sufficiently small perturbation size. So that's kind of, if you compare, for example, with Davis-Cahan, right? So remember Davis-Cahan, you have a matrix, you're adding a perturbation to the matrix, and you are saying, well, your eigenprojection changed by no more than a certain amount. How much? Well, if you have a perturbation of epsilon, basically your eigenprojection changes by no more than epsilon over lambda, when lambda is the eigengap. Now, here there is no eigengap, but there is, well, your perturbation size has to be sufficiently small, which is not the case in Davis-Cahan. So it's kind of a slightly different type of result. But if you look at the form of this, it's pretty similar to what you get for matrices. Okay, so that's the perturbation size. And now what you can actually show is that the convergence is in some sense fast. So when gamma is... So here you see that if actually gamma is close to 0, so this is the number of iteration, and the number of iteration basically is some sort of double log, and plus a constant which I'm hiding, you know, various things in this constant, but it's basically some sort of double log of the size of perturbation. You need that many iterations to converge to this error, and you can see when gamma is bigger than 0, that basically converges very fast. That's kind of analog of superlinear convergence. And when gamma becomes close to 0, well, what is happening, this becomes log base 1, and that's the case of x squared. And, you know, this becomes infinite. So in the limit case, you actually don't have this convergence. And of course, this is true, because, you know, if you're just doing power iteration for matrices, you would never recover other eigenvectors other than the main one, right? You would have to put some sort of orthogonality constraint for that. So that's what that is. So for example, if you just put gi of x equal x cubed, the kind of simple typical case, what you have is log 2, something like 1 over epsilon. So that's the fast convergence result. Okay, so maybe I should summarize. So summary. So first, there is a nonlinear, non-tensorial generalization of the classical spectral decomposition. Second, it's an efficient algorithmic primitive with some sort of superlinear convergence. And we provide theoretical analysis of an additive perturbation model and kind of analogs of Davis-Cahan type bounds. And finally, well, I think maybe just a kind of philosophical point. So that actually looks kind of differently on what makes power iteration works, right? In some sense, in ordinary power iteration, you have some homogeneity which gives you get a lot of mileage out of it. In this case, there is some sort of convexity, so it's not unthinkable, and the convexity which is not obvious from directly the problem. So it's not unthinkable that there are maybe many other problems in which there is some sort of hidden convexity which make things work, but which is not apparent when you sort of look at the problem itself. And I'll stop here.
Thank you.
One quick question.
So this hidden convexity picture didn't assume that the EIs are orthogonal.
So in this case, we need them to be orthogonal. It's a basis, orthonormal basis. Orthogonal is just as good.
But in your picture, it wasn't clear why you needed the orthogonality.
You mean here? You are saying if it's not orthogonal, this may still work.
So you won't be able to
It'll
count
still
the
be
number
convex.
but you won't be able to count the number of extreme points being so small.
Yeah, because you don't have, if you have, this is not going to be a correct map, right, if they're not orthogonal. We're using the fact that these coefficients are, this is orthogonal, right? This is some sort of Pythagorean theorem. But there is some trick, actually, we can do to deal with non-orthogonality, but not in a general case. I think in general you have to assume that it's orthogonal.
Okay, maybe just in the interest of time, we stop there. Just the organizers want me to tell you that we still start at 1:30 sharp in this room. Okay, for those that don't know, there's the business school over there. That's very easy to get some food and very quick. And there's also the law school, which is over there. That's probably the easiest. Okay, thanks a lot. Then.